welcome to the colloquium today, where Shutaro will tell us about the cooling flow problem, which is a very complicated issue involving supermassive black holes, gas cooling, and thermodynamics turbulence in the center of galaxy clusters. Shutaro got his PhD from Osaka University in 2014, specialized in X-ray and radio analysis of black holes. And then he became a postdoc at ASIAA, JAXA, until 2018. That's when he moved to IAA to work with Katie. And since then, he has been our go-to guy for anything related to X-ray analysis of extragalactic sources. And he was also very engaged in scientific activities like gallery and simulated meetings. So we were sad when his term was up this March, and we had a farewell party for him. And I still owe Casey $300 for that party. But after a few months of staying in Tsinghua University working with Karen Young, Shutaro was awarded most independent scholarship and brought it back to IAA. So let's give him a round of applause to welcome him back.
For very nice introduction to me. And also, I'd like to thank Ipa because actually he was one day asking me whether I can give a talk in working. Actually, yeah, since actually I'm a kind of like a newcomer of the IA, so yeah, actually this time it's very nice opportunity to give my recent research about galaxy clusters using not only X-ray but also ALMA observations. So, okay, this is the title of this talk. Yeah, and then this study is in collaboration with Keiji, and also some colleagues in Asia and also Japan. So this is the talk run today. Yeah, first of all, I'd like to briefly mention about what the galaxy clusters for just review, and going to the result. First of all, X-ray and ALMA views of protocols, and then systematic study using X-ray, and then future prospects like XRISM, which is a new generation X-ray telescope that will be launched in next year. Okay, so what is a galaxy cluster? So this is a X-ray and optical image of Coma cluster. Coma is one of the nearby galaxy clusters, and you can see in the background, you can see the optical image taken with SDSS. This is the so-called brightest cluster galaxy. It is the most luminous and massive galaxy in clusters. And this X-ray image from blue to red shows the distribution of diffuse and hot X-ray emitting gas, so-called ICM, intracluster medium. So actually you can see the ICM is filling in the galaxy clusters in intergalactic space like this. So they have no special association with galaxies like this. But the emission mechanism is different. So and also interestingly, the total mass of the galaxy cluster is of course dominated by dark matter. But this fraction is about 85%, it's super big. But the second one is not galaxies, but ICM. Actually, the total mass of ICM is about 30% in the galaxy clusters, and then contributions from galaxies only 2%. It's quite few. So in that sense, if we want to study the baryon in the universe to understand, for example, the evolution of the baryon in the universe, so then we have to focus on ICM because the ICM is a dominant component in baryons.
What does the color mean, the red and blue?
This corresponds to the brightness of the X-ray emission.
Just brightness.
Yeah, just brightness. Of course, brightness depends on density square. So then this like profile shows the density distribution or density profile of the ICM in cluster. Usually, in the center, density is the highest, and the other stuff is very faint. So let's focus on the BCT. So this is maybe one of the famous image taken by JWST, which is released very soon, already. And this is a very infrared image of galaxy clusters. And you can see this is a BCG, brightest cluster galaxy located at the center of the cluster. And then, as you can see, this cluster is biggest and then most luminous in the cluster. So actually, this is a image of the BCG. Of course, by definition, BCG is the most massive galaxy in cluster, but also one of the most massive galaxies in the universe. So then maybe this BCG could be special in the universe because, for example, so let's focus on the co-evolution between supermassive black holes and the host galaxies. So this plot shows the mass of supermassive black hole in center of galaxies as a function of stellar velocity dispersion, sigma. So this is proportional to the mass of galaxies, let's say. So then you can see this is the relation between the mass of supermassive black hole and the mass of host galaxies. And then the distribution of black hole mass is about 10 to 6 to 10 to 10 almost. And the BCG is located up here. So this very tiny correlation between these two parameters is well known as the co-evolution with supermassive black hole and host galaxies. Indeed, BCG is stand for this relation, but the relation seems to be more massive than the predicted by other galaxies. So these three data points show the data points of BCG, and they are deviate from this scaling relation. So what is the reason to make this like a deviation? So one reason is that the ICM can be maybe 12 of the mass black hole growth because in the galaxy cluster, the majority of baryon is ICM, not galaxy. If part of ICM can accrete into BCG and then accrete onto the black hole, then this deviation could be explained. And in some recent works mentioned that maybe cluster environments are maybe special and expected to be a very important role in growing supermassive black hole by numerical estimations. So one mechanism is called cooling flow. Since the X-ray luminosity here is proportional to density square here, so that means, or let's say X-ray luminosity is equal to the energy loss rate of the ICM. This data luminosity is very sensitive to density. And then this plot shows the cooling time calculated by this one, thermal energy over X-ray luminosity. Then it's a time scale of cooling time scale, cooling time. So this plot shows the cooling time as a function of the radius from the BCD. So here, this line shows almost age of the universe, about the 13.7 gigayear. And usually, age of cluster is expected to be, let's say, about 10 gigayear or so. So in that sense, actually, in the center of the galaxy cluster, the cooling time of ICM is very, very short, let's say, only a few tens megayear. So it's enough to cool by radiations because of this radiation. So, and also once ICM cools down, then actually density at the same region should be increased to keep pressure balance, because pressure is calculated by this equation, density times temperature. But if temperature decreases, then density should be increased. Then this kind of like inflow from outskirts to the cluster center could be expected. So this flow is called cooling flow. And also, since X-ray energy depends on density squared, so then this cooling, once cooling happens, then it's no longer be suppressed. So then runaway cooling is also happen in the cluster center. So then we expected that if once ICM cool down, and then expected star formation rate in the BCG is about 100 to 1,000 solar per year, which is quite enough for BCG and also for slow mass black holes. And importantly, this mechanism can work only in clusters, not in individual galaxies, because the presence of the ICM. So in that sense, ICM is very important for this cooling program and the growth of BCD and then supermassive black hole. But so we cannot see the cooling flow in the real galaxy clusters. So actually, this is a very famous temperature profile. So y-axis is the temperature as a function of the radius from the BCD, and then this is the temperature profile of the ICM in the Perseus cluster, which is also nearby galaxy clusters. So actually, in the outer region, you can see temperature is low and then going to high at certain point here. But interestingly, from the certain point, let's say about 100 kiloparsec, so temperature starts decreasing. This is what we expected, because X-ray radiation, so X-ray ICM emits X-ray radiation, then they lose energy like this. But interestingly, about here, temperature decline is stopping at here and become constant like this. So, but interestingly, ICM density is still increasing for the center. So then radiative cooling is still dominant at the center. So then we call this region a cool core. But inside the cool core, temperature starts decreasing, but stop like this. So this suggests that something is heating the ICM. Otherwise, actually we expected this temperature profile. Actually temperature decreasing towards center, but become constant in practical. And interestingly, this cool core is found in the very wide redshift range and also cluster mass range. So this is, let's say, cool core is very general properties of galaxy cluster. So then, eventually, the stable heating mechanism is required to explain this constant temperature profile for the center. So maybe one of the reasonable and maybe most plausible mechanism is so-called ASIAA feedback. So this is a famous picture of galaxy clusters, and you can see in the background, this is the optical image. You can see BCDs here, and then blue color shows distribution of the ICM, and also in the pink color shows the radio jet from BCDs. So you can see very strong jet is launching from the BCD. And then you can see large so-called cavity, which is relatively lower density region, like here. So this kind of like a jet can interact with ICM and then provide some kinetic energy to the ICM. So this is a plot showing a power estimated by jet as a function of the X-ray luminosity. So you can see this jet power is nearly correlated with the ICM luminosity, which means And then this dotted line shows like let's say one-to-one relation between power and power by jet and X-ray emission. So let's say then jet can be heating source, and then its power is enough to suppress or can heat ICM enough.
Sorry, if I ignore the blue points for lab 10, then there doesn't seem to be much correlation.
Yeah, indeed. Maybe so all of this in units of the 10 to 42. So again, this is the galaxy scale, and then maybe group scale, and then cluster scale. Yeah, so if we focus on this, but maybe still related is large scale.
So each data point is a galaxy cluster or group?
Yeah, including from galaxy to cluster scale.
So the lower left points are galaxies, individual galaxies.
Yeah, individual. But maybe massive galaxy.
But this is just a more and more. You know.
You mean the power?
Yeah, it's a smaller galaxy, bigger galaxy.
So maybe in this box, so maybe spiral
You
or
can put Jupiter on this plot, he'll be down there, it'll be on a straight line, right? Or the sun.
no,
No, this is jet power.
yeah,
The what?
jet power, jet.
Power from the jets.
Oh, there's some point in nebula we have jets too, we can put down there. 10 to 35, you know, it's good, yeah. Give you another slope.
Anyway, so but let's say so this is one of the indirect evidence that AGN feedback can heat ICM and the jet power is enough to suppress the cooling because jet power is comparable to the X-ray emission. But recently, if we focus on the very center of the cluster, we can see, of course, kind of like evidence of regime feedback, but also some other features, so-called gas thrusting. So actually, this is the position of the AGN in X-ray. So this is the X-ray zoom-in image of the particle cluster. And the scale is, let's say, 10 kiloparticle or so. So here is the AGN, and you can see the cavity here. So maybe if we see this region in radio band, so this is the radio emission contour. So this position of the jet is associated with X-ray cavities here and here. And interestingly, here we call bubble, like here. There's no counterpart in radio band, but still we can see the cavity in X-ray images. And also you can see that like a kind of large scale spiral, like here. So of course, this cavity and maybe this bubble is associated with AGN feedback, and maybe this jet can push ICM for the outer region. Then this jet make cavity. But in this large scale spiral, it cannot be explained by them. But also, this maybe spiral could be made by the margin, cluster margin. So in that sense, if we want to study any feedback system or heating source in cluster center, you have to focus all of the features observed in the X-ray images. And then, for example, this is a zoom out image of the galaxy cluster, but the same galaxy cluster, particle cluster. So this is the X-ray image taken with Chandra. Here is the center, and you can see some bubble here and cavity and bubble here and here. But once we subtract the mean profile of the X-ray images to emphasize substructures embedded in the X-ray images, so then we call this as a X-ray residual images. So residual means we subtract mean profile and then we can see this kind of like a profile. So you can see spiral here So this spiral is what we see in the previous page. So actually size of spiral is about 100%, so which is quite large compared to the scale of the ASIAA feedback, but still comparable to the size of cool cores. So then we could expected that this is due to the motion of the ICM, because this is a shape is spiral, so then maybe we could expect this kind of like a motion in the plane of the sky. And of course, this kind of like a motion could be generated by the past or ongoing cluster merger because of the translate of the angular momentum from the subcluster towards this primary cluster. So then this kind of like a spiral could be made.
So he told me measure the velocity field of
Yes,
this,
indeed.
and how does it look like?
I will explain very later, but let's say about 100 kilometers per second in gravity. It's slightly, let's say, rotated, but the velocity gradient is 100 kilometers per second.
And other than cluster mergers, are there other ways to explain the spiral feature? And
Yeah.
are these features common in full core clusters?
Yeah, indeed. So what I present here today. Okay, but maybe spiral is part of the morphology induced by mergers. So we could see maybe diversity of the perturbations, not only spiral but also some like campy structures. But this kind of like a perturbation is very common in cool cores. So then this mechanism is called gas crossing. So then gas crossing is the main topic of today's talk. And then this let me briefly introduce some characteristics of gas crossing. So this is another X-ray image of the galaxy clusters A1, H35. And then this is the X-ray image, and this is the X-ray digital image after subtracting the mean profile of the X-ray image. So then you can see this kind of a spiral. So this spiral is composed of two regions. One is a positive density excess region here, and then the other is a negative density excess region. So positive means density is high compared to the mean, and negative means density is low compared to the mean profile. So like this, and then also I did spectral analysis to measure the temperature of the ICM in this region, and I found that temperature is also different. In the positive excess region here, temperature of ICM is low compared to this region. But interestingly, pressure is like comparable to each other, suggesting the pressure equilibrium of the ICM in the cool core. But this is of course an indirect evidence of the pressure equilibrium. So now we have ALMA to observe the Swing-Yash relativity effect to see the cool core, or to see the pressure perturbations in the cool core. Because so actually the origin of the signal in X-ray and then Swing-Yash relativity effect is same. So actually ICM itself emits X-ray by thermal brainstorming. This is thermal emission. Then we can see the X-ray image in the X-ray light in X-ray. But also, actually, ICM is interacting with the cosmic microwave background photons. And then some photons is done by the impulse constant scattering. Then their energy is slightly different. So then we could see, and then so this is a radio band. So then we can see the Swing-Yash relativity effect in radio band, and then we can, and also this aesthetic effect is proportional to the pressure of the ICM. In X-ray humidity, X-ray humidity is really sensitive to pressure, but for aesthetic effect, aesthetic effect, this is sensitive to the pressure. So then, once we observe galaxy clusters using aesthetic effect, then we can directly see the pressure of the clusters. But of course, X-ray and the aesthetic effect is complementary to each other. So now we have an ALMA to see the aesthetic effect in the clusters. And then in this study, we use band 3 in the ALMA to observe aesthetic effect. But as you know, ASIAA is now constructing band 1, and band 1 is more powerful than band 3 to observe or to measure the aesthetic effect of the individual clusters very systematically.
So why is that? I thought the decrement is smaller to
Yeah,
a
yeah.
lower frequency.
But the sensitivity, okay, I will say, but the sensitivity of band 3 is relatively, how to say, low. So we spend, let's say, 12 hours to observe one galaxy cluster to see the aesthetic effect. But once, band 1 is available, then observing time is reduced. So this is the X-ray and the ALMA aesthetic views of two galaxy clusters. So one is a galaxy Z 1347. The other is a Phoenix cluster. So redshift is about 0.45 for this cluster, and for Phoenix, redshift is about 0.6. So this is the X-ray image taken with Chandra, and this is the image taken by the ALMA effect. So of course, the region is same. So you can see the morphology of X-ray image is consistent with the aesthetic effect like this. And also, ALMA observation is very important because ALMA boundary is capable of imaging aesthetic effect with almost 5 per second angular resolution, which is also comparable to Chandra resolution. So once we see the aesthetic effect like this, so then if we found substructures in aesthetic effect, so then that site is almost comparable to the Chandra, what we could see in Chandra image. So again, let's say X-ray image is very sensitive to the density profile of the clusters. So then you can see that this is maybe distribution of the ASIAA. And but for aesthetic effect, this is sensitive to the pressure profile of the clusters. So then this profile shows the global profile of the global pressure profile of the galaxy. So then let's do the residual analysis for these two images, two clusters. Then this is the result of the residual analysis. So we can see the residual in X-ray images. Like this is for RxCJ, and this is for the Phoenix cluster. In the RxCJ, so we can see clear spirals in the residual image, like this. And also southeast axis, like here. But interestingly, in the pressure, residual image of the pressure profile, or aesthetic, we can see the southeast axis corresponding to the X-ray band. But in the spiral region seen in X-ray, there is no association or no counterpart in aesthetic effect. So this is RxCJ, but if we focus on the Phoenix cluster, so this is the residual image of X-ray and the aesthetic effect. So you can see cavity can be found in the residual image here and maybe here, but in the aesthetic effect, we cannot see any features like spiral or cavity. So again, so pressure is SL detector is really sensitive to pressure. So if actually some mechanism creates pressure perturbation in the center of the cluster, then we could see that in the SL detector, but we cannot see any features like this. So interestingly, in the Phoenix cluster, so this cavity is really associated with radio jet found by groups. But in the end, there's no evidence of the pressure perturbations in the SL detector. And also, but let's say this excess is associated with cluster mergers. So this is a shock heated gas, but not associated with the region field. So to clarify this perturbation, so we solved the equation of the state for the gas perturbation. So the equation of the state is given by this W. W is delta P, delta pressure over delta rho. So for delta P, this is of course the SLT digital image. And for delta rho, this is from X-ray digital images. So if actually the mechanism to create this spiral is like adiabatic process, so then the square root of the W should comparable to sound speed, the ICA. But if isobaric, so this value should be lower than sound speed, the ICA. And for RxCJ, so we calculated this W using this digital images, and then obtain the upper limit for the pressure perturbations. So for the center, but in the calculation, we removed this southeast sector to calculate W. But in, let's say, in the center, corresponding to the spiral in X-ray images, there are no apparent pressure perturbations. Upper limit is about 700 millimeters per second. And then this is one of the most massive galaxy clusters. So then the temperature of the ICM is quite high, about 10 kV. So 10 kV gas corresponds to the sound speed of this 1600 km per second, which is quite higher than this estimated value. But interestingly, if we apply this method to the southeast excess here, then the estimated the W, square root of W is about 2000 km per second, which is almost comparable to the 20 kV gas here. And then we also again apply this method to the Phoenix cluster. Then the derived square root of W is less than 1000 km per second. It is also lower than sound speed of the expected ICM for gas perturbation. So then this result shows very nice and direct evidence of the isobaric nature of the gas perturbation in the cluster. But again, for this ALMA observation is very expensive. So we spend almost 20 hours to observe one single object. So if you are using ALMA, so then maybe you say that maybe 20 hours observation is quite maybe long. So it's not enough to see all of the clusters seen in X-ray camera. So then we have to do a systematic X-ray studies because X-ray observation is very cheap. And also in practice, actually we can see not only spiral patterns, but also very unique and special features in the digital images. And then this pattern is depending on the merger geometry. So this image shows the expected X-ray digital image once merger happens in plane of the sky or line of sight. So if merger happens in the plane of the sky, then we could see spirals like this. But once merger happens along line of sight, then we could see different features of gas perturbations like this. So this is a sample of the observed celestial images in X-ray band. So this is spiral, 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 but this is not spiral. But still, this one is corresponding to the maybe line of sight merger. So indeed, you have to do systematic study to understand the physics of cool quark in general. So then I and my colleague focus on two samples. One is a crash, and then the other is a high flux cluster sample. The crash is composed of the 25 galactic clusters. They are the massive one. And then actually the temperature by estimate higher than 5 keV, which is enough to say massive. And this redshift distribution is relatively moderate redshift distribution. So we extract 12 equal clusters from the class sample, and then for high flux class samples, they compose of the 64 galaxy clusters using lots of space surveys. They include not only galaxy clusters but also some massive galaxies and also galaxy groups. And then this catalog contains very nearby samples. Actually, the median of the redshift range is 0.04, which is very close to us. Then we can see more details of gas perturbation in cool quark clusters. So eventually we extract 28 cool quark clusters which have a cooling time of less than 1 gigayear, which is quite short. Then let's say more powerful heating mechanism is required to suppress the cooling flow. And of course, so both cluster samples are complementary to each other, and one of the well-studied representative samples. So this is a X-ray image and digital image of the crash, and then these are high flux samples of the X-ray image of the high flux samples, and then digital like this. So, but both results are same. So then I want to present the latest result, which is focused on the high flux class sample. So anyway, so this is the X-ray image. So you can see basically the distribution or shape of the X-ray image looks elliptical. But once we subtract the mean profile of the cluster, then you can see some like a diverse morphology of the digital image. For example, here you can see the spiral, but yeah, otherwise, actually, the morphology is quite diverse. So again, so by using the X-ray spectral analysis, we measure the density and temperature. So this is the density in the negative X region as a function of the density in the positive X region, and this is the temperature. So we can see the clear offset from the one-to-one relations. Actually, the ratio of density in both two regions are about 0.8, and temperature ratio is about 1.2. So this result is also consistent with numerical simulations done by Buffon and then Chandra. But yeah, okay, so pressure is calculated by density times temperature. So and this is a relation in the pressure. But if we plot high flux only, or if we put crash as well in the pressure profile relations, so we can see no pressure perturbation. So this suggests, of course, the ICM is in pressure equilibrium in the cluster center, even they have some morphology in the radial. And also, interestingly, so since no pressure perturbation found in the cluster. So then entropy distribution or the entropy perturbations can be used to estimate the motion of the ICM. So this is the plot of the entropy profile in the negative excess region, the function of the entropy in the positive excess region. We can see the clear offset from the unity, one-to-one relation. And then this is about 1.4. So this ratio can be converted into the 3D Maha number of the ICM. So then derived or expected Maha number of the ICM is about 0.3. So if that is 4 kb, then this Maha number corresponds to about 300 or 400 kilometers per second, which is consistent with direct measurement of the passes cluster by Hitomi collaboration. So in the end, this ubiquitous subsonic gas motion induced by gas lossing can be a really stable heating source to suppress cooling flow. So finally, let me briefly introduce new X-ray satellite, XRISM, and some future prospects. So XRISM is a recovery mission of the Hitomi. So actually, Hitomi X-ray observatory was launched in 2016, but some incident happened in space. Eventually, Hitomi was broken in space. We have no longer observed the galaxy clusters with Hitomi. So that's why XRISM is proposed to JAXA and NASA. And we are now facing very recent launch. Actually, XRISM will be launched in 2023, which is, of course, next year. And then XRISM will have a very good high resolution X-ray microcalorimeter. So this is not from X-ray XRISM, but taken by Hitomi for passes cluster. This is observed X-ray spectrum with the ICM. So to calculate as a function of energy, you can see clear ion lines, ion K-shell lines from highly ionized ion. And then you can see many lines corresponding to, for example, resonant lines, forbidden lines, and intermediate lines. And then, so then we can observe, or we can estimate, or we can measure the line width of each line, which corresponds to the target for ion site velocity dispersion, the ICM. So eventually, we will be able to observe gas motion with accuracy of about 10 km per second, which is quite nice. Actually, a factor of 100 times improved from previous estimate. Yeah, for example, this is just an example of the ICM emissions. So this is a theoretical model of the ICM emissions. Because since ICM contains out of the metal, so metal emit each specific X-ray line like this. So if we focus on the ion K-shell line here, this is expected from the model. So this is a simulated XRISM spectrum using this theoretical model. So if we focus on the ion K-shell line here, so okay, this is almost comparable to the theoretical model. So just in case, so let's compare with the current working Chandra observatory. So you can see this is a spectrum taken with Chandra. Yeah, ion K-shell line can be seen here. And then if we pick up this energy scale in the linear scale, this is the linear scale, this is the log scale. So you can see this very small curve corresponds to this one. Because of the energy resolution is quite large compared to XRISM. So then actually, yeah, indeed, so XRISM will be capable of resolving many lines like here, especially ion K-shell line, which is very important for physics of ICM.
What kind of simulation this is for clusters and population?
Yeah, I just assume temperature is 4 kb, abundance of 0.3 and the latitude is 0.
0.
So then compared to the sceptical. And also this is also same setup for simulation.
And how long is the observation?
1 megaparsec, no, 1 megasecond. It's enough to demonstrate the power of the XRISM. So then actually this is the review of the previous result by Hitomi. So actually we did a measurement of the velocity field using Hitomi. So this is this plot shows the bulk motion in the center of the pulses cluster. And this is the velocity dispersion, line of sight velocity dispersion I see in the same region. And then you can see some gradient. So the deep blue color corresponds to the blue shifted gas. And then this shallow one corresponds to the red shifted gas. So it's kind of a gradient. And the gradient scale is about 100 meters per second. And then if we see the line of sight velocity dispersions in ICM, so let's say, actually, ICM has a line of sight velocity dispersion of 100 kilometers per second in general. But in some regions, okay, the value become higher. So at least the very nearby region of the ASIAA and also Pavo region here. But otherwise, the velocity dispersion is quite like uniform in the cluster center. And then this, even this two region has larger line of sight velocity dispersion, but the factor is only 2, which is quite low compared to the expected by jet motion. Usually the motion or velocity of jet is over 1,000 km per second or more, but the observed one is quite lower than expected value from the agent feedback scenario. But of course, this is just example because of the Hitomi was broken already. So then XRISM will extend this kind of like a velocity measurement to many other nearby galaxies clusters. And also, so recently we found very like a strong and compact pressure excess in the center of the cluster. So this is the SD images. So you can see some very strong and compact SD effect in the center. But in X-ray images, we cannot see this kind of like a corresponding structure. So we take zoom images of this region, and then we take a contours, and the contours rotated, overlaid on the X-ray images. So you can see the peak of SD effect is slightly opposite from the X-ray peak or BCT's position. So this is the SDSS optical images. So you can see BCT is here, but the peak of the SD effect is slightly offset to the center of the BCT. Okay, size is quite small, let's say in 7 kiloparsec in physical scale. So again, so actually SD effect is sensitive to pressure. So they have two possibilities to explain this signal. One is the temperature origin. If ICM is heated by, for example, AGN very strongly and then locally, then ICM at this region heated up to a few 10 or 10 kV. The other scenario is that, okay, this is from density origin. But in X-ray images, we cannot see any counterpart in X-ray images. So that means, again, so X-ray velocity depends on the density squared. So if we have some very high density regions, so then we can see very significant X-ray flux to that source. But instead, actually, this peak corresponds to the cavity here, which is lower density region compared to the surroundings. So then this SDH suggests that maybe some very hot gas exists in the center, maybe due to the electric arc. So then this actually observation suggests cool core environment is not so simple, maybe super complicated than our thought.
So do you see radio jets?
For this cluster, no.
So how do you support this ICNTT by agent scenario?
Yeah, maybe. Yeah, but observationally, we can say this could be due to the temperature origin. Maybe required temperature is about 10 kV or more. But there's no special source to make such kind of high temperature component.
Is the BCG itself an AGN?
Actually, in radio band, we can see the strong radio emission. Maybe it's coming from AGN, but it's hard to say that is a jet. Because the size is quite compact, only 12 seconds, so it cannot be resolved in the image. And also one mystery cluster, so-called Phoenix, is found. So this is the HST image of the Phoenix cluster core. The size is about 50 kilopascals. 50 kilopascals. This cluster is discovered in 2012, very recently, and then one of the massive galaxy clusters. And interestingly, this cluster hosts very strong cool core, but the star formation rate, okay, estimated star formation rate is quite high, about 500 to 800 solar mass per year in the BCGs. So actually, you can see some filamentary structures in the HST images. This is due to the star formation activity in the BCGs. So in the end, so we don't know why, but the cooling flow happens on these clusters. So far, we believe that the cooling flow is no longer activated in the cluster center because of the presence of some heating source in the center. But only for the Phoenix cluster, they show some evidence of cooling flow as shows very massive star formation as evidence of the cooling flow.
What's that blue color thing? Those filaments, blobs. What wavelength is it?
O2, I forgot.
So it's
O2
a nebula light emission.
Yeah. Background is red is maybe, I don't know. But for blue one, this corresponds to O2 line emission.
Can you be sharp, excited? And for the ionized gas be sharp rather than heated by young cells.
Shocked by what?
Info emotion.
Maybe more.
It's option 2. It's a low ionization.
So interestingly, but yeah, that is a very important one. Interestingly, this cluster also have a strong jet found by the ASIAA observation. So the prediction of the launching jet is this. So actually, I was wondering that maybe this planetary structure could be associated with more prediction of the jet. Yeah, but yeah, partly they are heated by shock or other mechanisms. But yeah, actually, jet cannot suppress this kind of like a very strong or massive star forming activity in the BCG, at least for this class. And also, interestingly, the mass of supermassive black hole of this BCG up to 10 to 10, which is also one of the most massive supermassive black holes in the universe. So maybe this kind of like a property could be related or linked with each other. But still unknown. So then we have to investigate more. So then this is a summary of the topic. Again, so galactic cluster is very unique, like environment to study the very extreme physics of the universe. And then full core is found and formed in the cluster center in very unique. Actually, the distribution of the full core is very unique, very homogeneous and common in clusters. And heating source is required to explain observed temperature profile, but still the mechanism is unknown. AGN feedback is one of the reasonable scenario, but the gas machine can also help to suppress the cooling. And then to distinguish them or to study more, gas perturbation is very important Actually, we found that ALMA observation is very powerful to observe special perturbations in the cluster center, but eventually no perturbations. We did like a systematic study in X-ray band and found the isobaric motion, which is consistent with direct observations of the ICN in the passes cluster. So we spent a lot of time, but still cooling for problem is not solved yet. So we found new things, new findings, and then XRISM will be help us to like observe galactic clusters of gas motion or galaxy field very deeply. And also the complementary study is still ongoing. Yeah, so stay tuned. Yeah. That's all.
Thank you. Question.
You found this, you said the heating source is required, the gas solution. So what's the energy source for gas solution itself? So the gas is moving,
Yeah.
right? So what makes it move? Is it tidal interaction in the merger or something?
Actually, the source is merger. So once subclusters falling into the cluster, then angular momentum should be translated from the primary cluster.
Okay. So it's caused by
Some-
the merger,
yeah.
caused by the interaction. It's kind of a gravitational thing,
Yeah.
perturbation.
So then actually gas motion is also created, and the kinetic energy of such gas motion can be converted into the turbulence. Then turbulence can be heat.
Well, how come the overall ICM morphology looks smooth?
Yeah, that is a point that I'm using. So maybe first or minor merger could be the source of the transmission. Because once major merger happens, we can see the evidence of major merger in X-ray.
Well, it's like that you throw a rock into the water, the pond, the surface doesn't change anymore, but it has ripples. So you have to subtract the background to see the ripple, right? Because the overall, the distribution does not change much, only the ripple. So all these structures you see are just ripples. The background you subtract, that's the bulk of the majority of that, the bulk of the
Yeah.
gas. Yeah. So I'm just saying, if you want to see the ripple on the top of the pond, you throw a rock, you see ripple, you subtract the surface, right? You see only the top part.
Right, but okay, so suppose there's a small group falling into a cluster. Do you see any deviation of velocity distribution of galaxies from, say, the Gaussian, particularly in the center?
Yeah.
If we cannot see the signature in the gas, can we see the signature in the galaxy motion?
For example, BCG.
No, I mean, if the infalling group has its own dominant galaxy, I would like to know what's the relative time scale between the two galaxies that will merge, and for the ICM to come back to kind
the processing time scale is about 1 gigayear. So then maybe
Well, gas is easier to be pushed around. Galaxies cannot be easily pushed around. It's like, well, in one galaxy, the stars are collisionless, but gas is dissipated. So the gas would react differently from the stars. So when you have merger or whatever pass through, the galaxy itself doesn't change, but the gas reacts very violently. So you're seeing the gas reaction to the gravitational perturbation.
I mean, right, this is like, well, the picture you were describing is like a ordered cluster to me. So ICM will be dissipating, whereas the dark matter and galaxy will continue. So you may see some splashback activity of that inflowing thing. So the galaxy will come. The galaxies of the inflowing group may continue to its trajectory to the outskirts of the cluster.
So okay, this is the original image of the one cluster. So and then this contour shows the mass distribution taken by the strong wavelength analysis. So you can see some substructures very close to the center here. So maybe, and then this is already stripped gas by merger, like here, and then maybe trajectory of this substructure this way. So, but maybe the gas originally in the subcluster, stripped by gas in the primary cluster, but of course, dark matter halos can go through directly. So then eventually this kind of like a structure is dissipated by some interaction between the gas. But we could see some evidence in the motion of, let's say, dark matter halo of galaxy PCGs. So then this kind of like a spiral can be stable.
Shutaro, I think this is a bit peculiar case. This is a very high speed collision, very high temperature system. If you can mention the typical mass ratios for the gas flushing cases according to the simulation.
Let's say 10% of the primary cluster. It's let's say minor.
And there's a
Impact
parameter is
parameter.
size of the core radius. Yeah. So it's not really destroying the full core, unlike really the mass high-speed collision. But this really full core still exists. This kind of selection.
So this is animations from numerical missions, not by our groups, but done by Johnson. So this is the original temperature profile. So you can see the full core here, and the merger happens from this way. We can go. So then, gases start rotating, and then you can see some spiral structure in the beginning of the merger. But the time spent long time, eventually, the merger or secondary or third inflowing happens. Eventually, gases mix. But in the initial stage of the merger, we can see some spiral features.
Easy to have or
just to follow up this one that as you see there's this density contrast, so is that fraction of density variation consistent with the observations?
Okay. So we verify our method or our method using two types of numerical estimation. One is done by Chandra, our colleague, and also to home. So, but the observed density, observed ratio of the temperature is consistent with observation.
So my question is the clusters are overall still quite smooth. So are there still material inflowing from outside, or they're isolated and they are expected to get denser and denser?
Yeah.
The second.
So then actually gas sloshing is maybe naturally happen in the cluster because cluster is still growing by accretion from surrounding materials.
So there are still gas inflow.
Yeah. So then they can be heating source at the center.
So when you talk about crash and high flux clusters, you mentioned that you use X-ray observation to derive temperature and density, and then you get pressure. Then why do you
Pressure is
SD.
you have two unknowns, so you have to.
No. Not heat. In the page for the crash and high, whatever name it is, later you talk about temperature and the density, both from X-ray,
Yeah, that's what I said.
then you get pressure.
Yeah, but the problem of the X-ray element is, for example, line of sight depth is unknown, and this is projected, not projected. So some uncertainty is still included in the X-ray element. So that's why we need ALMA, SD.
Which doesn't have projection.
But they still have, but so actually we obtain two types of measurement, real time result. So then we can solve the equation of the state of the gas because so X-ray is sensitive to density and pressure. So then we can solve the equation for the state equation of the state.
And also in the very early slide, when you show the black hole mass and velocity dispersion relation, you suspected that BCGs are higher than the normal correlation, maybe because of cooling form.
Yeah, at that point, but yes.
But my question is, if gas can cool down, they, as you say, they may fuel the AGN, but they may also fuel star formation to increase the stellar mass.
Yeah.
So, are you suggesting that cooling to the parsec scale is more efficient than cooling to pure parsec scale? So AGN get fuel, but star formation does not. Is that what you're suggesting?
So if I stand for the AGN feedback scenario, so actually AGN feedback suppress star formation activity very effectively, the BCTs. But so to make very strong jet, so cold accretion is required. So then gas is more effectively accrete on the supermass black hole, but still star formation is suppressed according to the maybe latest scenario. So actually, I don't know. Let's say I don't know why, but maybe I think or cooling some part of the cooling flow can grow supermass black hole very effectively, but the still star formation is suppressed.
I think one possibility is that the BCG will merge with other massive galaxies, and black hole mass will grow this way. But for this minor mergers, the velocity dispersion of the BCG will not change much, and so you only increase in one axis, not in the other. I mean, this is old data. If you look at more recent compilation and focus on the BCG part, there is almost no correlation. I mean, if you hide the rest of the points, you will not say there is a correlation.
But for the new data, our BCG is still above the normal correlation.
Some BCGs have crazily massive black holes. Okay, I think this is a good one to stop. but Shutaro will be here for at least 3-4 years. Feel free to